So this is Unit 2 on polynomials. In 2.1, students will be able to identify key components of polynomials and perform basic operations on them. So our essential questions for this subunit are what are the key components of a polynomial and how are the properties of exponents used in simplifying polynomial expressions? So a polynomial is an expression that's written as the sum or difference of terms which are separated by plus or minus signs. So we're able to count the number of terms based on the number of plus or minus signs. So here are some examples of polynomials. However, there are four things that would make something not a polynomial. The first is you can't have a variable in the denominator. You can't have an x on the bottom. The second is you can't have a negative exponent. And what we'll see later with our rules of exponents is that having a negative exponent actually means that you have a variable in the denominator. So they're kind of the same requirement. The third one is that you can't have any variables that are radicals. You can't have any square roots, cube roots, fourth roots, etc. And lastly, again, even if there's an x or a variable on the top in the numerator, you still cannot have a variable in the denominator. So let's look at this multiple choice question. Which of the following is not a polynomial? So we're looking for one of those that doesn't fit our rules, or one that breaks one of our rules. So x cubed minus 1, there's no x in the bottom, it's not negative, there's no radical, so it is a polynomial. B also is a polynomial, but C is not because it's 2x to the negative 2, and like we said, we can't have a negative exponent. So let's go ahead and define degree, leading coefficient, and constant. As you can see by the picture, you can kind of figure out what these terms mean, but let's give them a formal definition. The degree is the highest exponent in the polynomial terms. It doesn't matter where it's located per se, but it's the one that has the highest exponent. The leading coefficient is the coefficient, or number in front of, that term with the highest exponent. So in this picture, 2x cubed with a degree of 3 is the biggest of all the exponents, and 2 is the number in front of that. So that's our leading coefficient. A constant is a fixed value, a number with no variables, which is 12. We can classify polynomials both by the number of terms and by its degree. So we're going to go through classifying by term first, and then we'll get to degree. If a polynomial has one term, we call it a monomial. These are some examples. If it has two terms, like a two-wheeled cycle, we call it a binomial. We'd call it a bicycle. Here are some examples. If it's a three-term polynomial, it is a trinomial. And if it's bigger than 3, we just call it a polynomial. If I wanted to classify it by degree, if it doesn't have a degree or it has a degree of 0, that's a constant. If it has a degree of 1, that's a linear, like y equals mx plus b. If it has a degree of 2, we call that a quadratic, like x squared. And if it has a degree of 3, we call it a cubic. All right, and if it has anything more than that, we haven't formally learned what to call them, but we did go over in class what a fourth degree was called, and that was called a quartic. So let's go ahead and identify the degree, leading coefficient, and constant for the following polynomials. So if I'm looking at x squared minus 3 minus x to the 6th minus 9x to the 4th, I'm looking for the biggest exponent, which in this case is 6. Now, because my biggest exponent is 6, my leading coefficient is the number in front of that, which is negative 1. You just see a negative sign, but that's because it's a negative 1. And the constant is the one that doesn't have an x. That's negative 3. So in the bottom example, what would be our degree? If you said 3, you're correct. Therefore, because our degree is 3, we're looking for the number in front. That is also 3. Now here's a trick question. Our constant is something that doesn't have an x, but there's nothing here that doesn't have an x, so our constant is just nothing. It's 0. In the bottom part, we're going to classify the following polynomials by its terms and its degree. So 5x has only one term. We call that a monomial. The degree is 1. There's only x to the 1, so that's a linear. In the second one, we have two terms, the negative x cubed and the 2. That's a binomial. And the negative x cubed, our degree is 3, so we call that a cubic. In the third one down, negative 12, that's all alone. It doesn't have anybody else, so it's a monomial again. And it doesn't have any x's, so we call that a constant. And the last one has 3 terms, so we call it a trinomial. And its degree is 2, so we call it a quadratic. General form, sometimes referred to as standard form, is when a polynomial is written in terms of its highest exponent first, followed by the other ones in descending order. So constants are always written last. In other words, if I have a cubic, I would have the cubic term, the quadratic term, the linear term, and then the constant term. So it kind of counts down. So in that case, it would be 3, 2, 1, 0. All right, so in these examples where we're supposed to rewrite the following expressions in their general form, identify the leading coefficient, and give it their names by terms and by degree, all right, I have 3 terms, so I know I'm calling it a trinomial. The biggest degree I see in that first example is the biggest exponent is a 3, so that one has to be written first. The second highest is the degree of 2, and then the last one is the degree of 0. So if I were to write this in general form, I would have x cubed minus 4x squared plus 3. My leading coefficient is the number in front of the term with the biggest exponent, so that's a 1. We already said the degree was 3, and we call that a cubic, and the number of terms was also 3, we call that a trinomial. In the bottom example, I see 4 terms, the x, the negative 4x cubed, negative 5x to the 4th, and positive 3. So that's going to be called a polynomial because it's more than 3. All right, our degree or highest exponent is 4. And we said on the last page, even though we don't have it written down in our notes, a 4th degree polynomial is called a quartic. And our lead coefficient is the number in front of that, which is a negative 5. So to write this in general form, it would have to be negative 5x to the 4th minus 4x cubed plus x plus 3. So to operate on polynomials, we must remember our exponent rules. So we're going to run through these real quick. Hopefully you've seen them before, but we'll give a couple examples of each. The first rule is the 0 rule. Anything to the 0 power is 1. 3 to the 0, 1. X to the 0, 1. 0 to the 0, 1. The second rule is the 1 rule. In other words, anything to the first power is itself. So you can just write it as the base. 9 to the first is just 9. X to the first is just x. 0 to the first is just 0. Next is the product rule. When I have two things with exponents being multiplied together, we add the exponents. So in our example, we have x cubed times x to the 5th. We add 3 plus 5 to get our solution of being x to the 8th. The quotient rule is the opposite. So if in multiplying I add the exponents, then in division I should subtract the exponents. So if I have x to the 11th over x to the 4th, my solution would just be x to the 7th. The power rule can sometimes get confused with the product rule, so let me make this very clear. When I have a power rule, I have something with an exponent being squared or cubed or raised to the 4th, 5th, 6th power. It's different than me multiplying two separate things with exponents. If I have something raised to a power, I multiply the exponents. So here I have x to the 5th cubed, which means I have x to the 5th times x to the 5th times x to the 5th, and that's going to give me x to the 15th. Next is the reciprocal rule. If I have x to the negative number or 9 to the negative number in this example, what I'm saying is that I really have 1 over 9 to the positive of that number. So in this one, it's 9 to the negative 2, which is the same as 1 over 9 to the positive 2, which gives me 1 over 81. The same rule applies if it had been In the denominator, maybe you had a question that said 1 over 9 to the negative 2. That would be the same as flipping that fraction and having 9 to the positive 2, which would give you 81. Lastly is our fraction rule. If you have something with a fraction, so x to the 1/3, what you have is the cube root of x to the first. So the denominator of the fraction denotes the type of root you are taking, and the number on the numerator of the fraction tells you what power to raise your base to. So 9 to the 9 over 2, x over 9 to the 2 is taking the square root because my denominator is 2, so that's the square root, and my numerator is 9, so inside I'm taking x to the 9th. Remember though, those, if you see them, make something not a polynomial. That's not allowed. So let's go over quickly how to add and subtract, multiply our polynomials. So if I want to combine like terms, I must be adding or subtracting. So if I am adding or subtracting, I'm not doing anything with the exponents. I leave them alone and I just add or subtract. So I want to find the perimeter of my quadrilateral. Well, perimeter means adding up all the sides. So I need to add x plus 1, x plus 4, x plus 1, and 2x plus 3. So I need to combine all my stuff with x's and all my stuff with no x's. So I see 2x plus x plus x plus x. That's going to give me 5 x's. And then I've got 4 plus 1 plus 1 plus 3. That's going to give me 9. So my answer should be A. In multiplying, you have two options. You can either use simple distribution, sometimes called foiling if you're multiplying binomials together, or you can create a box to help you organize your thoughts as you multiply and then combine like terms. So in this problem, we're asked to find the area of a rectangle. Well, area is length times width. So I'm multiplying 2x plus 1 times x minus 1. If I were to create a box and multiply everything out, I would get letter C as the correct answer. So here we have a bit of matching to kind of reiterate what all the definitions that we've learned so far. So in number 7, I'm looking for the definition of binomial. A binomial is a polynomial with two terms. So C fits perfectly. In number 8, standard form, sometimes called general form, was when I wrote my terms in descending order from highest degree to smallest degree. So that matches well with D. My lead coefficient was the number in front of the term with the highest exponent. So that's going to fit nicely with G, the number in front of the first term of a polynomial, assuming that that polynomial is written in general form. A monomial is a polynomial with one term, so A correctly matches that. Degree is the value of an exponent of a polynomial. It's the highest exponent that you see, so that matches with F. Our constant is a number that does not multiply any power of x. It doesn't have an x, so that choice is B. And 13 for trinomial, that's a polynomial with 3 terms. So the only letter that was not used was letter E, a polynomial with 4 terms, and we called a polynomial with 4 terms just a polynomial. In 2.2, students will be able to factor trinomials when A is 1 and when A is bigger than 1. In other words, we'll be able to factor all trinomials. Remember, trinomials meant 3 terms. Our question is, what's the relationship between multiplying polynomials and factoring them? So a trinomial is a polynomial with 3 terms. It looks like ax squared plus bx plus c. And factoring is simply the process of finding things that would multiply together to make that certain polynomial. So it's reverse multiplication or undistributing. There are 3 ways that we're going to look at, and quite honestly, I think that reading the steps is a lot more complicated than just looking at a couple examples. So we're going to look at a couple of examples. But let's go quickly through our steps so that we know a general idea of what we're going to do. In step 1, we're going to factor out a GCF, or a greatest common factor, if it has it. Then we're going to draw an x and put the product of a times c at the top, and we're going to put b at the bottom. In the left and right, we're going to put a times x with a fraction bar. We're then going to ask what multiplies to a times c and adds to b. We're going to put those factors under the fraction bar and reduce the fraction if we can. Then we will combine those fractions into our two binomials and check that we got the right answer. So here we go. In the first example, we have x squared plus 5x plus 6. My a is 1, b is 5, and c is 6. Again, we set up our x, and in the top, I need to put a times c, so 1 times 6. In the bottom, I need to put b, which is 5. On the left and right side, I need to put a times x, so 1 times x, which is just x. The magic question I need to ask is what multiplies to 6 but adds to 5, and those answers are 2 and 3, so I place them beneath the fraction bar. If I can reduce the fraction, I do. In this case, I cannot, so my two binomial factors are x plus 2 and x plus 3. So my final answer is the factored form is x plus 2 times x plus 3. In the middle example, I have h of x equals 2x squared minus 6x plus 4. If there's a GCF, I need to take it out. So in this case, our GCF is 2, so I'm going to factor a 2 out, leaving me with x squared minus 3x plus 2. My new a value is 1, my new b value is negative 3, and my new c value is 2. So when I set up my x, I'm putting a times c at the top, which is 1 times 2. In the bottom, I'm putting negative 3. And on the left and right side, I'm putting a times x, which is again 1 times x. Our magic question is what multiplies to 2 but adds to negative 3? Those numbers are negative 1 and negative 2. So in my x, I place negative 2 and negative 1 beneath my fraction bars. Again, if I can simplify the fraction, I do. In this case, I cannot. So my answer is simply going to be 2, which was my GCF, times x minus 2 times x minus 1. On the far right-hand side, I have g of x equals 3x squared minus 2x minus 5. I have my a value as 3, my b as negative 2, and my c as negative 5. When I set up my x, I'm putting a times c at the top, so I'm putting 3 times negative 5 at the top. I'm putting b on the bottom, and again, I'm putting a times x on either side. Our question is what multiplies to negative 15 but adds to negative 2? I'm running through all the factors of negative 15 in my head. Negative 15, 1, negative 1 and 15, negative 5 and 3, negative 3 and 5. And I'm adding them up in my head to see which one of those options would give me negative 2. And the answer is negative 5 and 3. Therefore, if I can reduce the fractions, I do after I put those magic numbers on the bottom. I can't reduce 3x over negative 5, so that stays, leaving one of my binomials as 3x minus 5. However, 3x over 3 is the same as 1x over 1, so I can simplify that binomial to x plus 1, so that my answer is g of x equals 3x minus 5 times x plus 1. Here are a couple additional problems for you to try. The second one is a lot more tricky than the first. However, the first one does have a GCF, while the second one does not. So in the first, my GCF was 12, which means I'm going to take out a 12 and leaves me with z squared minus 2z minus 3. Our magic question is what multiplies to a times c but adds to b. So I want you to go ahead and try these two problems on your own. Keep in mind that the second one has some large numbers, so you're going to have to try a lot of factors before you find the right one. The second method that we're going to talk about is called the reverse box method. So again, our first step is to always factor out a GCF. Then we're going to draw a 2 by 2 box and put the first term in the upper left and our C term or last term in the lower right. We're going to ask our magic question and place those factors in those two remaining boxes. Then we'll take out the GCF in each column and in each row, and that will give us our. So these are the same three problems but before, so we're going to get the same answers as we did before. However, we're going to do it through a different method. We've identified our A, B, and C values. I've put my first term, x squared, in the top left box. I put my constant in the bottom right. I'm asking myself what multiplies to 6 and adds to 5. Those numbers were 3 and 2, so I placed 3x and 2x on either side. And then we take out the GCF in each column and each row. If I'm looking at the first column, I have x squared and 2x. Both of them have an x, so I put that on the top. In 3x and 6, they both have a 3, so that's my GCF there. In the top row, I have x squared and 3x. Again, my GCF is x, and 2x and 6 both have a factor of 2, so I pull out a 2. I then combine what's on the outside, so I have x plus 2 and x plus 3, so those are my binomials giving me my factored form. In the middle, I again factor out my GCF, where I have 2 times x squared minus 3x plus 2. I have identified my a, b, and c values, and I've placed my first term in the top left, my last term in the bottom right. What multiplies to 2 and adds to negative 3, that's negative 2 and negative 1. Notice that there is a typo that should read what multiplies to 2. We've placed those values, negative 2 and negative 1, in our remaining boxes, and now it's time to take out the GCF in each column and in each row. In x squared and negative 1x, the GCF is just x. In negative 2 and 2, my GCF is negative 2. In the top row, I have x squared and negative 2x. My GCF, again, is x. And in negative 1x and 2, my GCF is negative 1. Therefore, I have to remember to put my GCF back, but my factored form is 2 times x minus 2 and x minus 1. In the third example, there is no GCF, so I simply identify my a, b, and c values, and I've already written my a term in the top left, my c term in the bottom right. Our magic question again is what multiplies to negative 15 and adds to negative 2. Those numbers were negative 5 and 3, so I went ahead and filled those into the 2 remaining boxes. Now it's time to take out the GCF in each column and each row. So if I'm looking at the first column, I have 3x squared and 3x. Both of those have a 3 and an x in them, so that's my GCF. In the second column, I have negative 5x and negative 5, so the GCF is negative 5. In the top row, I have 3x squared and negative 5x, both of which share an x. And then I have 3x and minus 5, which have nothing in common, so I just take out a 1. I combine those outsides together to get my 2 binomials, so I get g of x equal to 3x minus 5 times x plus 1. The last method that we're going to talk about is called grouping. To me, it makes the most mathematical and logical sense. Again, we're going to take out the GCF if we can. We're going to ask our magic question, and then we're going to rewrite the trinomial as a 4-termed polynomial, replacing the middle term with the 2 terms that we are coming up with in step 2. Then we're going to pair the first 2 and the last 2 terms together and take out the GCF of each pair. Then we'll combine our GCFs into a binomial, and then we'll keep one of the things in parentheses. So for grouping, in the top left, I have x squared plus 5x plus 6. I've identified my a, b, and c, and I've asked my question of what multiplies to 6 but adds to 5. Those numbers are 3 and 2, so I split my trinomial into a polynomial by breaking my b term, which was 5, into the corresponding pieces, 3x and 2x. I then pair up my first 2 terms with my second 2 terms and take out the GCF of each. If my stuff in parentheses is not the same, that means that I must have messed up at some point. But because both of my parentheses are the same, they're both x plus 3, I've done it correctly, and therefore the final step is to take the outside 2 terms, the x and the plus 2, combine them into a binomial, and then take one of those that are in parentheses and leave it as x plus 3. In the middle example, we do know that my GCF is 2. When I factor it out, I get a new a value, b value, and c value. My question is what multiplies to 2 and adds to negative 3. Those answers were negative 2 and negative 1. We rewrite the trinomial as a polynomial with 4 terms by breaking that middle term into 2 corresponding terms. So we have 2 times x squared minus 2x minus 1x plus 2. We pair the first 2 and the last 2 terms and take out the GCF of both. Again, my stuff in parentheses is the same, so I have not screwed up, and therefore the final step is to combine the GCFs into a binomial and take one of those that were the same in the parentheses. In the final example, there was no GCF, so my a value was 3, my b was negative 2, and my c was negative 5. Our question was what multiplies to negative 15 and adds to negative 2, and that was negative 5 and 3. We then rewrite our trinomial as a polynomial. Notice that it does not matter the order in which the b terms are written. I could have written 3x squared minus 5x plus 3x minus 5. In this case, I just chose to write 3x squared plus 3x minus 5x minus 5. The order does not matter. Again, I repeat the same process where after I've paired the first two and the last two terms, I take out the GCF of both. I notice that my things in parentheses are the same, so I have not messed up, and thus my last step is to take the outside GCFs, combine them into a binomial, and leave one of those that is in parentheses. In subunit 2.3, again, we are continuing our factoring. However, we're going to factor difference of squares as well as the sum and difference of cubes. Our essential questions are what term is missing in a difference of squares or cubes question, and what does the acronym SOAP stand for? So in difference of squares, it is something that is a squared minus b squared. Both of our numbers should be perfect squares. If they are not, it means we have a GCF that we need to take out. So in step one, we need to take out a GCF if we've got it. Then we need to take the square root of both of our terms, and then plug in our square rooted terms, a and b, into our parentheses to form our factored form of a plus b times a minus b. And lastly, we can double check. So in the far left, we have x squared minus 9. Both of those are perfect squares, so we can skip step one. There's not a GCF. In step two, we're going to take the square root of both of those. So our square root of x squared is just x. Our square root of 9 is 3. So we plug those into a plus b and a minus b to get x plus 3, x minus 3. In the second one, we have 36x squared minus 1. Again, both of those are perfect squares, so we do not have a GCF. We take the square root of each, and we get a to be 6x and b to be 1. We plug those into our a plus b, a minus b equation to get 6x plus 1 times 6x minus 1. In the third example, though, 2 and negative 32, they are not perfect squares, so we have a GCF, and in this case, our GCF is 2. So if I pull out a 2, I'm left with x squared minus 16. Those are perfect squares, so again, I can take the square root of both, plug them into my equation, and I can't forget to put back my GCF in my final equation. So I have 2 times x plus 4 times x minus 4. Again, in the far right, I do have a GCF because in this case, 32 is not a perfect square and neither is 98. So I'm going to have to factor something else out. And once I do, again, that factor is going to be a 2. I'll be left with 2 times 16x to the 4th minus 49. If I take the square root of both of those, I get 4x squared as my a, and I get 7 as my b. So my answer is going to look like 2 times 4x squared plus 7 times 4x squared minus 7. In sum or difference of cubes, we either have a cubed plus b cubed, as in the case of sum, or we have a difference of cubes, as in a cubed minus b cubed. We need to first take out our GCF, if there is one, and then we need to take the cube root of each term. Taking the cube root on our calculator is saying math 4, enter, and the cube root means blank times blank times blank equals that number. Plugging in a and b into our parentheses will give us our correct form of the equation. And notice that our letters are the same. The pattern is a squared, ab, b squared. However, our signs change, and that comes with the acronym of SOAP, same, opposite, always positive. The first sign is the same as the problem. The second sign is the opposite of the problem, and the third sign is always positive. So in the top right, we have x cubed minus 64. There is not a GCF, so we take the cube root of both. The cube root of x cubed is x. The cube root of 64 is 4. We then plug that into our equation, which looks like a difference of squares. So it's going to follow the b subpart in number 3. So I'm going to have x minus 4 times x squared plus 4x plus 16. In the bottom left example, we do not have a GCF again. I would like you to change it to being 8x cubed plus 27 so that we can see a sum of cubes. We're going to take the cube root of both. The cube root of 8x cubed is 2x. The cube root of 27 is 3. And then we need to plug that into our sum of cubes formula. So we're going to get 2x plus 3. And then we have a squared. So we have 2x squared, which is the same as 4x squared, minus a times b, which is 6x, plus 3 squared, which is 9. On the far right, though, 250x to the fourth and 128x are both not perfect cubes, so there must be a GCF. In this case, our GCF, or greatest common factor, is 2x. They both have an x, and they both have a factor of 2. When we take that out, we're left with 125x cubed plus 64. Those are perfect cubes, so we can take the cube root of both, and then we need to plug them again into our equation. Notice that my answer again has switched from being a difference of cubes to a sum of cubes. So please make sure that your signs are appropriate according to the question that you are solving. If you are solving a sum of cubes, then keep it as the answer you see on the page. If you are doing a difference of cubes, your answer should read 2x times 5x minus 4 times 25x plus 20x plus 16. In subunit 2.4, we are learning how to solve polynomials. We are able to find the zeros, x-intercepts, solutions, or roots of polynomials. Those are all interchangeable. When I say to find the x-intercepts, it's the exact same thing as if I were to ask you to find the zeros, or the exact same thing as to find the solutions or the roots. I'm a big fan of Big Bang Theory, which is why I've put this meme down on the far right. Our essential questions are: how is factoring related to solving polynomials, and what is the quadratic formula? To solve a factorable polynomial, like the ones that we've been doing, you set each of those factors equal to 0 and solve for x. However, sometimes we can't factor, so a function is not factorable. And to solve functions like these, we utilize the quadratic formula, which is x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Solutions to the quadratic formula that involve I are named complex solutions, and the complex number system includes both real and imaginary numbers. So I will sing you how I remember the quadratic formula once before we talk about I some more. It goes along with the theme of Pop Goes the Weasel, so here we go. X equals negative b plus or minus square root of b squared minus 4ac all over 2a. I've remembered it since 9th grade, so maybe on the test you'll be singing that song in your head. Now, on the right side, there's a box that has I squared, I cubed, and I to the fourth. I, as a value, is the square root of negative 1, so I'd like you to write the square root of negative 1. I squared is negative 1. I cubed is negative I, and I to the fourth equals 1. So the pattern is I, negative 1, negative I, 1. And then it repeats. I, negative 1, negative I, 1. In 2.5, division, we are able to divide polynomials using both long and synthetic division, and we are able to interpret the meaning of a remainder. So our essential question are: what are the limitations of using synthetic division? So we divide polynomials using a method similar to long division, so we need to review that first. We have 277 divided by 12. So first we need to set up the division. Then we need to ask how many times 12 goes into 27. And we're going to put that number in the top. Then we're going to multiply 12 by that top number and place it below. We're going to subtract, and we're going to bring down the next term and do it again. So I've set up my division. I have 12, which is my divisor on the outside, and I have my dividend, which is 277 on the inside. I ask myself how many times 12 goes into 27. The answer is 2 times, 2 whole times. So I put 2 at the top. I then multiply 2 times 12 and place that number below. So 2 times 12 is 24. And then I subtract. 27 minus 24 is 3. And then I bring down the next term, which is a 7, and I repeat. How many times does 12 go into 37? The answer is 3. So I get 3 times 12, which is 36. I subtract and I get 1. So 277 divided by 12 is 23 with a remainder of 1. Think about when you ask yourself how many times the outside number goes into the inside number, think about it like division. How many times, so if I were to divide 27 by 12, what whole number would I get? 27 divided by 12, I would get a whole number of 2. So that's the number that goes on top. Long division follows the same steps. The only reason it's more complex is because we're using polynomials instead of ordinary numbers. So we're going to set up our division with our divisor on the outside and our dividend on the inside, and then we're going to work through the examples. If there is a term missing, we have to put a 0, and we'll see that in a couple of our examples. So in the first, we have x cubed minus 2x squared plus 6x minus 6 divided by x minus 3. X minus 3 is our divisor, so it goes on the outside. And the big long polynomial is our dividend, so that goes on the inside. All right, our question is, we then have to divide the inside term by the outside term. So we have x times what equals x cubed? Or x cubed divided by x equals what? And that number goes on top. So x cubed divided by x is x squared. So that number is placed on top. Then we multiply x squared times x and x squared times negative 3 and place those numbers underneath. Then we subtract. X cubed minus x cubed is nothing. Negative 2x squared minus negative 3x squared is going to give us negative 2 plus 3, which gives us positive 1x squared. We bring down the next term, which is 6x, and we repeat. X squared divided by x is just x, so we place that number on top. We then multiply x times x and x times negative 3 and place them underneath. We subtract x squared minus x squared and get nothing. And then we have 6x minus negative 6x, we get positive 9. We then bring down our next term. 9x divided by x is 9, so we put a 9 on top. We multiply 9 times x and 9 times negative 3, and we subtract. 9x minus 9x is nothing. Negative 6 minus negative 27 is positive 21, so our remainder is 21. Notice how I wrote the remainder. We wrote it as a fraction. Be aware, you should be able to recognize the remainder being written as a fraction over the divisor, as well as simply R21. Both of them mean the same thing. In the far right example, again, we follow the same steps. So see if you can kind of put those together before we progress into the next example. Here we have 3x to the third minus x minus 7 divided by x minus 2. That means that we're missing a quadratic term. We go from an exponent of 3 to an exponent of 1 to an exponent of 0. We have to make sure that all of our exponents are accounted for. So it can't go, we have to insert a 0. So we have 3x cubed plus 0x squared minus x minus 7. Those are called missing coefficients. Then the process is still the same. So keep in mind you have to fill in zeros if something is missing. In the far right, again, we have something missing. However, this time our thing that's missing is in our divisor and not in our dividend. So in our divisor, we have x squared plus 0x plus 1. The process is again the same. Synthetic division is a shorthand way of dividing polynomials by a linear binomial. In other words, our divisor has to be a linear binomial with a coefficient, a lead coefficient of 1. Our steps, we need to first set up an L and place the number of the divisor on the left and then the coefficients of the dividend on the inside. We bring down the first term, we multiply it by k, and we place that product on the diagonal, so under the next term. We add down, and then we repeat. Again, please note that you can only do division synthetically if and only if the divisor is a binomial, it is linear, and it has a lead coefficient of 1. So these are the exact same questions as before. However, we are now using synthetic division. So I have x cubed minus 2x squared plus 6x minus 6 divided by x minus 3. I place the opposite of what I see on the left side of my L. I see my divisor as having x minus 3, so I'm going to put a positive 3 on the left side. On the inside, I'm putting my coefficients, so I'm putting 1, negative 2, 6, and negative 6. I bring down the first term, which is a 1. I multiply it by 3 and place it on the diagonal, and then I add negative 2 plus 3. Then I repeat. 1 times 3 again, I place that number on the diagonal and I add those down to get 9. Then I multiply 3 times 9 and I put that product under the negative 6 and I get a remainder of 21. So my answer, my remainder is 21, my constant is 9, my linear term is just 1x, and my quadratic term is 1x squared. In the rightmost example, again, I place positive 7 on the left. I put my coefficients on the inside. I bring the first term down, multiply it by my outside number, place that number diagonally, add, repeat, and get my remainder to be 7, my constant to be 4, and my linear term to be 1x. To me, it's easiest to create your solution by working backwards, from the remainder upwards, rather than trying to guess the degree of the first term down. However, notice that my answers are 1 degree smaller than my dividend. So on the left side, my dividend was x cubed. My answer is x squared. On the right side, my dividend was x squared, and my answer is just a linear. In the last one, again, if there is something missing, you have to put a 0, but it still follows the same pattern. We get our remainder to be 15, and we work backwards. Again, we follow that same pattern of having our answer be 1 less degree than our original dividend. In 2.5, we're looking at higher order polynomial theorems. So we're going to be able to apply the fundamental theorem of algebra, the rational zeros test, the remainder theorem, the factor theorem, synthetic division to higher order polynomials such as the linear factorization theorem, and then we're going to be able to graph. How is long and synthetic division related to other polynomial theorems and graphing polynomials? The fundamental theorem of algebra, or FTA, states that if f of x has a degree of n and n is bigger than 0, then f has at least n zeros in the complex number system. So, according to the FTA, this polynomial would have 4 zeros in the complex number system. In the second one, since our degree is 3, it would have 3 zeros in the complex number system. The rational zeros theorem, or the rational zeros test, states that if coefficients are integers, then the possible zeros of that polynomial have the form p over q, where p is the factors of the constant and q are the factors of the leading coefficient. So we're going to list the possible zeros using the rational zeros test for j of x. P is the factors of the constant. In this case, my constant is negative 18, while q are the factors of the leading coefficient. So I'm going to set up a fraction, and I'm going to see all of the possible factors of each. P, which was the factors of negative 18, I can get negative 18 in a bunch of different ways. I can do 1 times 18. I can do 1 times negative 18. I can do negative 1 times positive 18. I can do 2 times negative 9. I can do negative 2 times positive 9. I can do positive 3 times negative 6, and I can do negative 3 times positive 6, which is why you see all of those plus or minus numbers. However, for my leading coefficient, my Q term, the only way I can get 2 is by multiplying 2 times 1 or negative 2 times negative 1. So once I've set up that fraction, I need to divide all of the numerator possibilities by the denominator possibilities. So I'm going to take plus or minus 1 divided by plus or minus 1, plus or minus 2 divided by plus or minus 1, plus or minus 3 divided by plus or minus 1, plus or minus 6 divided by plus or minus 1, plus or minus 9 divided by plus or minus 1, and plus or minus 18 divided by plus or minus 1. Then I need to take all of them and do it by 2. So plus or minus 1 over plus or minus 2, plus or minus 2 over plus or minus 2, which simplifies to 1, which we already have, so that's okay. Plus or minus 3 over plus or minus 2, plus or minus 6 over plus or minus 2, which becomes plus or minus 3, plus or minus 9 over plus or minus 2, and then plus or minus 18 over plus or minus 2, which simplifies to plus or minus 9. I realize I'm saying plus or minus an awful lot, but hopefully you can follow the way in which I'm creating my possible zeros. In the second example, my lead coefficient is 3, so my Q, or factors of my lead coefficient, are going to be plus or minus 1 and plus or minus 3. Those are the only ways I can get 3. Positive 3 times positive 1, or negative 3 times negative 1. My P is the factors of my constant, which is 4, and I can get 4 a variety of ways. I can do negative 1 times negative 4. I can do positive 1 times positive 4, and I can do positive 2 times positive 2, or negative 2 times negative 2. Then I need to set up my fractions. So I'm going to take all of those P values and divide them by Q. So I should get plus or minus 4 over plus or minus 3, plus or minus 2 over plus or minus 3, and plus or minus 1 over plus or minus 3. Then I need to take all of my P factors divided by 1, plus or minus 1. So I have plus or minus 4 divided by plus or minus 1, plus or minus 2 divided by plus or minus 1, and plus or minus 1 divided by plus or minus 1. The remainder theorem states that when a polynomial is divided by x minus k, the remainder is f of k. So if asked to find the remainder, using the remainder theorem is a lot faster than trying to do division all the way down to get the remainder. So if we are asked in this example to evaluate the remainder when it's divided by x minus 1, I'm going to plug in positive 1 into my equation and get my number as being negative 40. So my remainder would be negative 40. In the second example, I'm asked what the remainder is when I divide that polynomial by x minus 3. So I'm going to take positive 3 and plug it into my polynomial and simplify. So I have 3 cubed minus 2 times 3 squared plus 6 times 3 minus 6. So my remainder is 21. In the third, I need to plug in 7 into my equation and simplify. And lastly, I would need to plug in 2. The factor theorem states that if, when I plug in k into my f of x, the remainder is 0, then x minus k is a factor. So if I get 0 as my remainder, then it is a factor. So we're going to show that x minus 2 and x plus 3 are factors. So I'm going to plug in 2 into my equation, and I should get 0. And I'm going to plug in negative 3 into my equation, and I should get 0. In the bottom example, if I want to determine if x minus 7 is a factor, I need to plug in positive 7 into my equation. And if indeed the remainder is 0, then it would be a factor. And if it's not 0, then it's not a factor. The linear factorization theorem states that a polynomial will have the same number of factors as its degree. So the degree tells us how many factors I'm going to have. In this case, our degree is 4, which means I'm going to have 4 factors. And we know from the previous page that 2 of them, x minus 2 and x plus 3, are already factors because we use the factor theorem on both of them. So I can use synthetic division to slowly whittle down my fourth degree polynomial, which we call a quartic, down to a quadratic. Because remember, each time I do synthetic division, my degree of my answer decreases by 1. So when I divide by 2, or when I synthetically divide by x minus 2, I then am left with 2x cubed plus 11x squared plus 18x plus 9. My remainder was 0. Then I divide again by my x plus 3 term, and I get down to 2x squared plus 5x plus 3. Once I have a quadratic, I can factor that trinomial using any of the 3 methods from before. If you prefer the magic x, do the magic x. If you prefer grouping, do grouping, and if you prefer the box, use the box. Once I've factored, I now have all 4 factored forms. So I can combine those into my factored polynomial. Then if I want to find the solutions, or the x-intercepts, or the zeros, or the roots, I need to set each of those factors equal to 0. So in this case, we're given that x minus 1 is a factor. So we're going to do synthetic division to then simplify that cubic down into a quadratic to where we can factor it and find our remaining 2 factors. Once we've done synthetic division, we're left with 3x squared minus 7x plus 2. And when I factor that, I get x minus 2 and 3x minus 1. So my total answer, my factored form, is going to be x minus 1 times 3x minus 1 times x minus 2. If I wanted to find the solutions, the roots, the x-intercepts, or the zeros, whichever you would like to call them, I need to set each of those pieces equal to 0. X minus 1 is equal to 0 when x equals 1. 3x minus 1 is equal to 0 when x equals 1/3. And x minus 2 is equal to 0 when x equals 2. In 2.6, we were graphing polynomials by identifying key features from its equation. And our question is, how are the solutions of a polynomial illustrated on the graph or in the graph? In this example, we're asked to find the x and y intercepts of x squared plus 3x plus 2. To find the x-intercept, we need to set our y value equal to 0 and solve. So if I set my y value equal to 0, I can factor that polynomial into x plus 1 and x plus 2 and solve for when it equals 0, -1 and -2. I then can write my x-intercepts as 2 points, -1, 0 and -2, 0. To find the y-intercept, I need to set all of my x's equal to 0. So I'm going to plug in 0 everywhere I see an x, and I get y to be 2. So my y-intercept would be 0, 2. Graphically, you can represent the x-intercepts as where it crosses the x-axis, and the y-intercept as where it crosses the y-axis. Here's another example to calculate the x-intercepts and the y-intercepts. To calculate the x-intercepts, again, we would need to factor this polynomial into x minus 10 times x plus 2, which means if we set those both equal to 0, our intercepts would be 10, 0 and -2, 0. Our y-intercept would occur when our x value is 0. So everywhere I see an x, I'm going to put a 0, and I would get my y-intercept to be 0, -20. End behavior describes the behavior of a graph as x approaches a positive or negative infinity. We look at the highest degree of the polynomial and its coefficient. So if the degree is even, like x squared, x to the 4th, x to the 6th, then both of our ending points, either at positive infinity or negative infinity, are going to be in the same direction. If it's a positive leading coefficient, they're both going to end upwards. If it's a negative leading coefficient, they're going to both end downwards. The easiest way to remember this is like positive x squared looks like a u. Negative x squared looks like a hill. For odd degrees, if it's a positive leading coefficient, it starts down and left and moves up. It slopes upwards. If it's a negative leading coefficient, as it approaches infinity, it gets more negative. So it starts high and ends down low. So we're going to sketch the end behavior of these two just to solidify our understandings of end behavior. We have a positive leading coefficient and an even degree. So that's going to mean that both of my hands or arrows are going to be facing upwards. If I have negative 4x to the ninth, I have an odd degree and a negative leading coefficient, which means on the left side, I'm starting way up high and I'm ending way down low. Turning points are points on the graph where the function changes from going up and to going down, or from going down to going up. These are relative minima or maxima. We can't say that they are maximums and minimums because our graph is going to go on forever and ever and ever, so we don't actually have a minimum or a maximum. So to determine the maximum number of turning points, you calculate n minus 1, where n is the degree. Some functions may have fewer turning points than that number calculated, but that's the biggest number of turning points you can have. So if I have a fifth degree polynomial with a negative leading coefficient, I know I'm going to start high and left and move down and right. But I'm also going to go up and down. I'm going to have 4 turning points because 5 minus 1 is 4. So it's going to look kind of like a funky looking hill, I guess you could say. All right, and if on the right-hand side, when I want to draw a rough sketch of an 8th degree polynomial with a positive leading coefficient, I'm going to have both of my ending points be upwards. However, I'm going to have 7 hills. Systems of equations refer to sets of equations with the same unknowns, and the solutions are the point of intersection. A point, remember, is x comma y. At this point, both graphs share the exact same x and y values, and a system can have an infinite number of solutions, a finite number of solutions, or no real solutions. So an independent system has a finite number of intersections, in other words, a finite number of solutions. A dependent system is where every point intersects with each other. In other words, the functions overlap one another, or they're the exact same line. So that way they have infinite number of intersections. An empty set is a system where there are no points of intersection. So parallel lines, for example, would be an empty set. Again, these are our parent functions, but it also kind of demonstrates our turning points. So if I have a degree of 0, I have no turning points, it's just a constant. Degree of 1, again, no turning points, it's linear. If I have a degree of 2, we call it a quadratic, and I have 1 turning point. I have 1 little u. If I have a cubic, I have 2 turning points. If I have a quartic, I have 3 turning points. And if I have a quintic, or a degree of 5, I have 4 turning points.